Welcome everybody. We're gonna solve the following problem with application of derivatives to physics. So we consider a body that moves along some coordinate line, and we have the position function s of t being equal to t to the fourth minus 2t squared plus 2. We consider this only for positive time, and the units for the position are in meters and time is measured in seconds. So the first question is to find the acceleration of the body. So we remember that acceleration is the rate of change of velocity, and velocity is the rate of change of the position function. So to find velocity, we do derivative of the position function. So do it term by term. Derivative of t to the fourth gonna be t for t cubed. Derivative of negative 2t squared is gonna be negative 2 times 2t. And derivative of 2 is just flat out 0. So the velocity function becomes 4t cubed minus 4t. And then acceleration is derivative of velocity, or second derivative of position function. So take the previous formula and do derivative of that. We're going to get 4 times 3t squared minus 4. So derivative of 4t cubed gives us 4 times 3t squared. Negative 4t, derivative of negative 4t gives us negative 4. So simplify it a little bit, we get 12t squared minus 4. Okay, so that's the acceleration of the body. That's the formula for that. To answer the next question, when will acceleration be 0? So when refers to time. So we're going to set acceleration equals 0 and solve for time. We have 12t squared minus 4 equals 0. So solving that for t squared gives us that t squared is equal to 4 over 12, which is 1/3. So then t is going to be equal to positive or negative square root of 1/3. And since we only consider positive time, the only useful value to us is going to be square root of 1/3, the positive quantity. So that's when acceleration is going to be 0 at this time. So then when is acceleration positive or negative? Well, we're going to use test points. So we know that acceleration is flat out 0 when t is equal to square root of 1/3, which is about 0.57. And our time, the acceleration begins at t equals 0. So we need some test point between 0 and about 0.57. We're going to use 0.1. And to the right of 0.57, there is a test point of positive 1 for time. So at t equals 0.1, we evaluate acceleration. So we get 12 times 0.1 squared minus 4. We're using this formula for acceleration. And we end up having negative 3.88. So at this point, acceleration is negative. So since acceleration is never 0, between 0 and square root of 1/3, acceleration is going to be negative everywhere for time between 0 and square root of 1/3. And time equals 1, we can evaluate acceleration. We end up having positive 8 for the acceleration at 1. So it means that to the right of square root of 1/3, acceleration is going to be positive. So we answered those two questions with one approach. Welcome everybody. We're gonna talk about the two problems that use derivatives in the context of economics and business. First problem talks about marginal revenue of an airline. That's the problem to the left. So the problem says that this airline has the following revenue function. Revenue depending on the price of the ticket is 10,000 tax minus 100 tax squared. So we're looking for the marginal revenue function. That's derivative of the revenue function. Then gives us derivative of 10,000 tax minus 100 tax squared. Then gives us 10,000 minus 100 times 2x. So derivative of x squared is 2x. So we have 10,000 minus 200x. Now we're going to evaluate the marginal revenue at 49, 50, and 51. So marginal revenue at $49 gives us 200. Marginal revenue at $50 gives us 0. And marginal revenue at $51 gives us negative 200. So what in this context marginal revenue means? It means the amount revenue that we will bring in if we increase the price of the ticket, if we increase x, which is the price, by $1. And those calculations suggest that at the price of $49, if we increase it, we expect to bring in $200 more. At $50, if we increase the price, we expect to bring in nothing. And at $51, if we increase the price by $1 more, we expect to actually lose money. We expect to decrease the revenue. So let's see. So it appears that increasing the price to be above $50 per passenger does not really increase the revenue. So it's probably not something that you would want to do in this situation. Okay, that's what the marginal revenue is actually used for. Now, if we look at the problem on the right, so we talk about marginal profit. So we have the function for the profit that happens to be this complicated cubic polynomial. It has negative really small number times x cubed plus smallish number times x squared plus 80x minus 70,000. In this case, x is the number of TVs being produced. So we'll look for the marginal profit function. We're doing derivative of that monster. So we're looking at negative point, a bunch of zeros 2 times derivative of x cubed, that's 3x squared, plus 0.016 times 2x plus 80 minus 0. Okay, so this ends up being negative 0.000206 times x squared plus 0.032x plus 80. So then, once we have the marginal profit, we can plug in 2,000 units. X is 2,000 here. That's the number of units. So plug in x equals 2,000, crunch all the numbers, and we get 120. So what it means? It means that increasing the production from 2,000 units to 2,001 units will likely bring in additional $120 of profit. So that's what marginal profit is telling us. So if we go from production level of 2,000 units to about 2,001 units, we expect to get about $120 in profit.